Okay, morning year 10. So today we should have been starting our sound topic. So you should have already seen my instructions on the post on Google Classroom, but I'll go through here what you need to be doing anyway. So the first thing you need to do is spend a decent bit of time learning the spellings on page 90 in your notes. Then I need you to do a couple of the experiments. So we can't really do this stuff here that is on page 91 or the stuff on page 92 because I'm sure you don't have tuning forks at home. If you happen to, then fire on ahead with that page, okay? But what we can do is the experiments on page 93, so that's the stuff with the ruler. So I'm sure you have a ruler at home and a table that you can use. So just follow the instructions on that. So the thing that you all like to do in class anyway, hold the ruler down on the bench so that it about 20 centimeters hangs off the edge, and then do the wobbly ruler thing and write down what you notice. So I want you to fill that all in yourself after doing the experiment. Then as best you can give page 94 a go as well. So the tubes of water, you might be able to do that with glasses of water. All you need to do is fill your glasses of water up with different amounts. So the taller and skinnier the glasses that you have, the better. But say you had 4 different glasses of water and you filled them up by like those different amounts, then you'll be able to hear a difference in the sound that you hear. So do spend some time giving it a go. Okay, the rubber bands, you might be able to do that one if you have any rubber bands at home. Okay, so do those now. Pause this video, do those, and then play me again, and we'll go through what you hopefully did find whenever you were doing this. Okay, so I've turned back to page 93 just to make sure that we filled in our notes appropriately. So I'll fill in mine and you can check yours and then fill in anything extra. So the first thing it's asking you to do is hold the ruler down so that 20 centimeters hangs over the edge. Push the end down a little and then let go. So I'm going to do that. I have a ruler here. So if I hold down the end, and hopefully you'll be able to hear this, push down and let go. What do you notice? So, 2 things. The ruler vibrates up and down, and makes a noise. The vibrations make a sound. Okay. So for number 3, we had to repeat step 2, pushing the ruler down a bit further and then let go. So I'll do the original one again here. So here is my original one. And then pushing the ruler down a bit further. Hopefully you notice that one's a wee bit louder. So when pushed further, the sound is louder. Then repeat step 2 with a shorter length of ruler hanging over the edge. So again, here was mine with 20 centimeters over the edge. And then if I go shorter, and if I go from longer to shorter, we should notice the difference. So do you hear the difference in the sound in that? So if we're thinking about the pitch of the sound, do you notice how it starts off quite a low pitch? Oh, that was a good one. Let me try that again. So if I start here, do you notice that as well, you can't see what I'm at with my ruler, but as the bit of ruler that's hanging off the end of the desk is getting shorter, the pitch gets higher, it becomes higher pitched. So with a shorter length of ruler, the sound is higher pitched. And then for 5, the longer length of ruler is going to be lower pitched. So you can probably barely hear that one. Low, as I get shorter, gets higher. So the sound is lower pitched. Okay. Okay, with this one here, I'm probably going to be a little more general in our descriptions. So whenever if you give this a go, you should have found that to make the sound louder or quieter, all you had to do was blow harder or less. So blowing harder makes the sound louder. And different amounts of water in the tubes make different pitched sounds. It's not actually really the amount of water that we should be talking about there, it's the amount of air that's in the tube, but we'll not worry about that just for now. Okay. Down in the conclusion bit, all sounds are created by vibrations, so make sure you get that filled in. All sounds are caused by vibrations. So if we were in class, I would have shown you this. I'm sure you would have enjoyed making a mess of my room. The tuning fork, you maybe don't even know what a tuning fork is, wouldn't blame you. But it's like a little thing like this with 2 prongs, and these 2 prongs at the end vibrate, and it just makes a sound of a particular pitch or a particular frequency. Right, but if we had one of those and we dip it into water, then you can actually see the vibrations, because whenever they're vibrating really fast and you don't notice them. But if you dip them in water, then it like squirts the water about the place, so it shows the energy transfer that's taken place at the end of it. So the big thing we need to learn about this is that all sounds are caused by vibrations and particles vibrating. Like me speaking right now, my voice box is vibrating to make the sounds. That's all sound is. Okay, so page 95, we need to fill it in as well. What materials can sound travel through? Can sound travel through solids? Yes. How do you know? Well, if I hit a solid, you can hear the sound. If you put your ear down on the desk that you're leaning on at the minute and hit the desk, you'll be able to hear it, and you'll hear it actually much louder than you will just through the air. So don't deafen yourself or anything, but do give that a go. Put your ear down on the desk, give the desk a wee knock, and you will hear the sound much, much louder. Also, like, you can hear sound through walls and things. So if you're in one room in your house and someone else is in another room, you'll still be able to hear the sound through the walls. So let's write that down. We can hear sound through solid materials. E.g. walls. Can sound travel through liquids? Yes. How do you know? If something makes a noise underwater, we can still hear it. If you are swimming and you make a sound under the water, or you are under the water and someone else is and they make a sound, you can hear it. So let's put that down as our reason. How do we know? We can hear sounds. Oh, I've accidentally written that as if it's one word. Underwater. Okay. Can sound travel through gases? Again, yes. How do we know? Well, the fact that you can hear me right now, I'm just talking into air, which is a gas, and the microphone in this is picking it up, and then it's playing out of a speaker or whatever you're listening to it on. So we can, how do you know? We'll write down that as an example. We can hear people talking. Okay. Can sound travel through a vacuum? So remember, a vacuum is just whenever there's no particles at all. It's not a solid, it's not a liquid, it's not a gas, it's absolutely nothing, no particles at all. So no. It's like that saying about how you can't, what is it? You can't hear someone scream in space. Something like that. But no, sound cannot travel through a vacuum. And there's a little, I'm going to attach in with this as well a video. It's actually a Mr. Ross video of him demonstrating that sound can't travel through a vacuum. Let's just write down what a vacuum is. So vacuum is nothing. It is when there are no particles at all. Oh, sorry, that's slightly off the screen. Okay, so over this page is the little demonstration that again we would have been able to do in class, but now we can't. So what I need you to do is to pause this video and then click the YouTube link to Mr. Ross's video where he demonstrates carrying out this experiment just the way we would have done it in class. Okay, so watch that and then come back here and we'll fill in our answers. Okay, so hopefully you've watched that video from Mr. Ross, and then all these different parts will make sense to you. So what we had in our setup is a little bell, and this wee electromagnet bell with this big container over the top of it and a tube which connects to a vacuum pump. So what happens, it's just like a vacuum cleaner, it sucks all the air out. So with this tube attached here, it sucks all the air out, and then we end up removing all the air slowly but surely from this area here. So we end up with a vacuum, we end up with this little pocket of nothing. And what you should have noticed in the video, that it was actually, I think in the video it's a buzzer noise rather than this wee backwards and forwards bell. But what you should have noticed that was as the air started to move out of the chamber, then the sound coming from the wee buzzer got quieter and quieter and quieter as there was less air particles. And then eventually, whenever it became a vacuum, there was no sound at all. So let's answer in here. Teacher will set up, pretend we've done it, you've watched the video on it. With the air still in the jar, what do you hear? We hear the sound of the buzzer. So as the air is gradually removed, what do you notice? The sound gets quieter and quieter. When all the air is removed, what can you hear? No sound. So what does this demo show us? It shows us that sound cannot travel in a vacuum. Now, the reason that sound can't travel in a vacuum is explained a little bit using these diagrams. So before I ask you to fill this out, I know some of us got this done in class last week, but a lot of us weren't then. So I will give you a chance to get this filled out here today again. So sound actually travels the best through solids. Okay, so if we think back to what's actually happening with sound, sound is just particles vibrating backwards and forwards and backwards and forwards. So with a solid, because they're so densely packed together, the sound travels from particle to particle really, really, really quickly because they're all packed further together or closer together. With the liquid, the way the particles are slightly more spread out, sound doesn't travel quite as well in a liquid because, like, if you think about this one here, it has to travel all the way over here to get to this one to pass that vibration on. It's kind of similar to, if you remember in year 9, whenever we're learning about conduction in the heat topic. So because the particles are more spread out in a liquid, the sound energy doesn't travel through the vibrations quite as quickly. Then in a gas, because the particles are really far apart, then it again doesn't travel quite as well in a gas. So if you imagine if there's no particles in a vacuum, so there's nothing here, then the sound can't travel at all. Just doesn't work. Sound requires particles, and if there's no particles, it cannot travel. So this is page 97. Hopefully you've been following along with me if you've been filling in your notes. Pause the video and answer this sheet if you haven't already answered it. Okay, so here's my answers, or how I worded my answers in this. Hopefully you can read it. So pause this and check your answers, or I'm going to talk through it anyway. So I suppose you may as well just leave me rambling on here while you check yours. So I've tried to match up in my rows here so that all the comments match each other, and I've just taken my information from the table up above. So for a solid, the particles are very close together. In a liquid, they are close together rather than very close together, and in a gas, they're very far apart. The next one is particles held together with strong bonds in a solid. Liquid, they're able to move about, and in a gas, the particles can move easily in all directions. Here I went for how the sound vibrations can move. So in a solid, sound vibrations move quickly. In a liquid, they move more slowly. And in a gas, they move even slower. And then on the bottom one, I talked about how easy or hard it was for the vibrations to be passed on. So in a solid, it's easy for the vibrations to be passed on, and that's because of all these reasons, because the particles are very close together. In a liquid, it's a bit harder for the vibrations to be passed on, and then in a gas, it's even harder for the vibrations to be passed on. And again, that's directly related to how far apart the particles are. Okay, so if you haven't got all that checked, remember to pause it at any stage to make sure you can correct your answers. Okay, so page 98, there's a few questions for you to answer. So work your way through that, and then we'll go over the answers. So again, pause me and answer the questions, and then we'll answer them. Okay, hopefully you have yours answered. Let's go through the answers. So how do sound waves travel? They travel by passing energy along through vibrations. So passing energy along through vibrating particles. So what does vibrating actually mean? It means if something's moving backwards and forwards about the same point. So moving backwards and forwards about a point. Which picture are the particles furthest apart? That was in the gas. Which picture will the sound travel quickest? That's whenever the particles are closest together, so that's the solid. Explain why sound travels quickest through the solid. Because the particles are really close together. So in a solid, the particles are packed tightly together so the vibrations pass easily. Well, let's word it that way. From particle to particle. Okay, sound cannot travel through a vacuum, and explain why. There's no particles. So there are no particles to pass on the vibrations. Put these in order of how fast sound travels through them, and start with the fastest. So the fastest is going to be the solid, which is the rock. Then we've got water. in air, and then space. It just won't travel in space at all because it's a vacuum. Why do you think sound travels faster in steel than it does in wood? Steel must be more dense than wood, so if it's more dense, particles are closer together. So steel is more dense than wood, so the vibrations pass on more easily. It's probably terrible English, is it? Because the particles are closer together. Okay, that is us for today. So we'll leave this stuff here for next week. I am going to attach another YouTube video about sound that will probably be a little bit more interesting than listening to me, but that's us for today's work. Okay, so I will see you next week.